Is a Swede who got a PhD in Italy. That's quite a story. And then since then, burst onto the scene as an amazing researcher who's done fantastic work in approximation algorithms, including on asymmetric traveling salesman, which now he's finally solved, at least one approximation, which is probably one of the major open problems in this.
Thank you so much. Very nice introduction. So it's a pleasure to be here again. So I was here before, then I talked about the symmetric traveling salesman problem. So I broadened my research. So now I'm going to talk about the asymmetric traveling salesman problem.
Which was a question everybody was interested
in
40 years, yeah.
So, so this is joint work with Jakob, who is my student, and Laszlo, who is at LSE in London. So let me start by maybe answering a question you've been worrying about. So it turns out there's a lot of pubs in the UK. So 24,727 pubs in the UK. So now what's the shortest distance you have to walk in order to have a beer in each pub? So do you have any clues? What would be the distance you need to walk to visit every pub in the UK?
And cheapest is distance, you mean?
Cheapest in distance, yeah. No, I suppose since you have to have a beer in each one, the price will be constant, so in distance. No clue. Actually, I don't remember, so I think it's some millions. Yeah, it's 45.5 million meters something. And we know the answer thanks to Cook et al., who solved this instance to optimality in 2015. So it's pretty impressive. So you know, they know the answer because they solved the traveling salesman problem. So here, it was pubs in general. We want to find the shortest path of n given city. So here I have 7 cities in Europe. You have pairwise distances. Can you find a tour at every city at least once? That could be one example. Okay, so yes, this is a classic problem. Some variants were studied by these gentlemen, so Hamilton and Kirkman in the 19th century. Today it's like a well-known benchmark problem in computer science, but it remains, an interesting open question what we can achieve an efficient computation. I think both from a heuristic standpoint. So the example I showed with the pubs, they use a basically cutting plane method. So they solve a linear program and they add cutting planes to get to an integral solution. And today we're going to be focused on the TCS question, like what's the best approximation error? So what guarantee can we achieve in polynomial time? Okay, so when we study the problem, there are 2 basic versions. So there's a symmetric, where we assume that the distance from U to V equals the distance from V to U. And the asymmetric, where you make no such assumption. And that's the general case we're going to consider here. Okay?
Oh, I see. So the pubs is asymmetric because of one-way streets? Or?
No, I will cover one-way streets. Or I have a better, but that's a good motivation here in Princeton. But in Lausanne there is other good motivations. So this is Princeton is pretty flat, but Lausanne is pretty hilly. So it's easier to go downhill than uphill. Or if you're not convinced, it's much easier to ski downhill than uphill. That would be like asymmetric distances. Or one-way streets, maybe it's more convincing as Sanjeev proposed.
So the distance still satisfies the triangle inequality, but it's not asymmetric?
Yes.
And why the triangle inequality then?
Why the triangle inequality? Because otherwise you can do nothing.
The natural thing is I think, if you think about flights, it's sometimes cheaper to go through a connection. So that's actually a really realistic thing. So
perfect.
Forget about the triangle inequality, but assume that the distance from x to y is in some 100 or some constant time the distance from x to z plus the distance from z to y.
Oh, okay. Then you're probably also fine. Then
that's the kind of thing that
I would say it's also natural to say that so the triangle inequality only matters if you insist that you should visit every vertex exactly once. But if you insist that you should visit everybody at least once, which would be the case with flights, right? So you would be happy to make a hop, then it's equivalent. So you could think of the distance satisfying nothing if you're just visiting every city at least once, instead of exactly once.
I'm not sure it's the same thing, but you just the 2 things.
Okay, we're going to look at least once. We can discuss they are the same thing afterwards. Okay, so here's the definition. So we are given an input as edge-weighted directed graph. And so here is an example. So this is 1, 3, 1, 5,000. And you want to find a, so here I'm in a tour, so I said that we want to find something that visits every city at least once. So here, for example, we visit at least twice. Okay? So now we are debating, we already debated this case, because maybe you think of triangle sales problem as you're given a complete graph and you want to find a Hamiltonian cycle of minimum weight. So unless you have some assumptions on the distances, you cannot achieve any guarantee even for the symmetric case. So what people usually assume is the triangle inequality. Okay? And if you assume the triangle inequality, this version is equivalent to the one where you're given a complete version. Okay? I don't know if you meant that you have like relaxed the triangle inequality. Then it's not. This is the same thing as having the triangle inequality.
Again, if you relax.
Then it's no. Then I don't know. Yeah. But this is the same as the triangle inequality. Okay. Any questions on the problem? So this is the problem. You can think of this as a road network with one-way streets or different costs on different directions. You want to find a tour that visits every city at least once. So we want to look at the same definition but a little bit more graph theoretic. So what do we mean by a tour? We mean that we want to find a set of edges so that the graph is connected, so everything is visited. Okay? We want to find the edges of the tour so that it's connected and it's Eulerian. So here Eulerian means that the in degree is equal to out degree of every vertex. So this means that you're given a graph, you're allowed to remove edges, you're allowed to take any number of copies of an edge. At the end of the day, you want to have a graph that is connected, you visit every vertex, and the in degree equal to out degree. So that's an equivalent definition. It's a little bit more graph theoretic. Is that fine? Okay. Did I answer your question or did I confuse?
Neither.
Okay. All right, so this is the problem we're going to consider. So just accept this fact. Otherwise we can stop now. Okay, good. All right, so this is the question. So what do we know? So yeah, let me just give you some historical view of the approximation, what we know in terms of approximation algorithms. So remember, a row approximation algorithm is an efficient algorithm that on any inputs, it's a worst case guarantee, it's guaranteed to find a solution of at most raw times the cost of the optimal solution. So I will talk mostly about ATSP, but you know there's a very beautiful algorithm for a symmetric case, who is from 1970s. So this is by Christofides. So he showed that a certain algorithm gives a 1.5 approximation algorithm. And this is still an open question. Can we do better than 1.5? Okay. I guess that's one of the major open questions. And the same decade, there was another interesting development. So Hell Karp, they proposed a heuristic for calculating a lower bound on the tour. So I can tell you, hey, you have to spend at most this amount of money or this distance to visit all these cities. And the way they calculate the lower bound coincides with the value of a linear program that we will use. So it's called the Hell Karp subtour elimination relaxation. And you know, this happened in 1970s, and what is intriguing here is that there's a long-standing conjecture that this way of calculating a value of a tour or low bound of a tour actually gives a 4/3 approximation. So we believe that we have already an efficient algorithm that gives us a 4/3 approximation on the value of a tour at least, but we're unable to prove so in a symmetric case. And as we will see in the symmetric case, there's a very similar situation, but with a much larger gap. Okay. So in the 80s, we got the first approximation for the symmetric case. So it's a very elegant algorithm that I will have the chance to cover later on. So it's called the repeated cycle cover approach. So it's a log-based 2n approximation. So notice that there is no hidden constant. It's really a log-based 2n approximation. So in the 90s, there was not too much in ATSP, but Sanjeev and Mitchell, they have celebrated work giving a p-test, so arbitrarily good approximation guarantee, assuming that the distance are from Euclidean space. Okay?
Low dimension.
In low dimension. So now, you know, at this point of time, I think it was open, could we get a p-test for any TSP instance, even for asymmetric. So this was proved in 2000 that you cannot do. Okay, so it's hard to approximate the symmetric and asymmetric within some very small constants. So what we know about these problems are very far from what we know in terms of lower bounds, computational lower bounds. Okay. And we had to wait till also 2000 to get the first improvement for ATSP based on a very simple repeater cycle curve approach. So it was hard work, yeah. It was a little bit fun. So Blaise, so he proved it was a 0.99 log base 2 and approximation algorithm. So I don't know the historical context of this, but I can imagine, around this time there was a natural logarithm approximation algorithm for set cover, or we still have, and it was proved that you cannot do better. Even the hidden constant is the right one. So this result here shows that the kind of log base 2n is natural, as we will see later on, but that's not the right answer. So the world record here is by figuring they get a 2/3 log base 2n. So why do I mean world record? So all these approaches is based on the approach by Friesca, Alberti, Maffioli. So we will see it later on, but it's basically a bottom-up approach. So remember, we wanted to find an Eulerian graph that is connected. So let's forget about connectivity and just find a Eulerian graph. So for example, a cycle cover that connects part of the graph, and then we iteratively connect more and more of the graph. So all these approaches are based on that. And I suppose that's the best based on that approach. And in 2010, Asapuro managed to improve this. And they did so by introducing a new influential approach, okay? So their approach is very related to Christos Fides' approach, which means that you first select a spanning tree and then correct the parities, or here you correct the in degree and out degrees. So you first make sure that your graph is connected, and then you fix the parity, so in degree and out degree. And they defined, in a symmetric case, you don't have to worry so much, but in the asymmetric case, you have to define the tree you select has to satisfy some special properties. So that's called something they call fineness. And they use this connection to give the first asymptotic improvements, log n over log n. So that was basically the status a couple of years ago. So MP-hard could do better than 75 or 74. Best diagram has a super constant approximation guarantee. And as I said in the beginning, it has a very similar status as a symmetric case, but with a bigger gap. That we believe that the linear program actually gives a 2 approximation. So, or at least it was conjectured to give a constant, but let's conjecture that it gives a 2. And that would match the best known low bound. So we only know that if I solve a very natural linear program relaxation, we cannot do better than 2. But 2 seems like a good guess for the right ratio. Okay. So I have this very scientific comparison. I thought so, the progress on ATSP versus mobile. So here I have the year, and here I have the approximation guarantee of ATSP. So we have a log base 2 and it's 80s, and here is the mobile phones in the 80s. And then you can see the progress of mobile phones and the progress of ATSP. So here we have now we got the log n over log n. So I don't want to miss, that's a beautiful result, very nice, but I don't want to misrepresent it. That was the progress. So it was a tough challenge.
Maybe you should have shown the watch ones.
Yes, yeah. Oh, then I would lose my job. It's very bad for Switzerland. Yes, okay, so a little bit more serious. Sorry?
Progress and cuckoo clocks halted a long time ago.
I see. So yes, so there were 2 approaches. This is based on easy to find on Eulerian graph, bottom-up approach. I forget about connectivity. I iteratively ensure connectivity. World record is 2/3. Then a new approach that says, hey, let's first do connectivity and then fix the Eulerianicity. And this was then log n over log n. And then further evidence that this is a good approach was by Oscar and Saberi. So they gave a constant factor approximation arm using the fin tree relation for any bounded genus graph. And then more recently, like in a major progress, they showed how to use this approach to give a polylog log n, pretty heavy machinery to get a polylog log n bounded integral gap. So I write bounded integral gap because we don't know how to do this rounding in polynomial time. Okay. So around the same time, I introduced a third approach that is more related to the cycle curve approach, but a little bit different, and use this approach to give a constant factor approximation in a special case of no-weighted metrics. Yes, I call this local-connectivity ATSP, but it doesn't matter. So now you can think, okay, suppose you want to address the ATSP. So, you know, this approach has been around for a while. A lot of smart people have tried to push it. Seems like a bad idea to start over here. This is newer, quite some smart people. So you could still pursue this strategy. And here it was like only me that tried. So it felt like good to continue here. So what we did was to work quite hard, and then it was kind of difficult. So with Jakob and Lasse, we got first a constant factor approximation arguing for 2 different edge weights. And there we thought it was over because it's a pretty complicated paper. But then, as the title says, you know, we managed to get a constant. So why did we manage? I think the biggest difference was that instead of applying this approach immediately, we realized that we can do a sequence of reductions that simplify the problem we have to address. Okay? So the key idea that differs this paper towards what we try to do in the 2 edge weight is that we will do a sequence of reductions giving more and more structure to the instance. In the end of the day, we will have so much structure that we can solve this reduced local connectivity ATSP. So you can see that the constants are big, so 5,500. You could optimize it by losing, so it's very modular at the moment. You can read one part independent of the other. If you want to optimize it, maybe you could get down to a couple of hundreds, but you need new IDs to get close to 2. Okay, yes, it's a long path. So this is the sequence of reductions. I hope I will make sense of them during the talk. So first, we will use LP duality to say that, okay, although you're giving me a graph with arbitrary edge weights, these edge weights I can assume have very nice structure. Okay?
So this was known? This
yes, okay. That's classic. Well, yes, it's classic, but you will see that we use it a slightly different. It was known, definitely. So
what is this again? What is the statement?
I will tell you. So I will explain. So yes, that we use LP duality to get a special structure on the weight function. This is known as unused. So it has been used previously. A lot of, we will see. The uncrossing technique has used a lot in primal roundings, like Kamal Jain's paper in survival network design and so on. There has been few papers that have used it in the dual to characterize the objective functions you have to look at. And that's what we do here. But yes, this was known. And then there's irreducible instances. So here we will see that basically a recursive approach will allow us to concentrate on very special instances. Vertebrate space, we use the node weighted result to get down here, and then we just solve it. So hopefully I will be able to explain to you that we come to something with so nice structure, so you will go home and believe that this you just have to be able to solve. Okay, so let's start with the first. Oh yes, so I have a goldfish, because it looks frightening. There are 4 steps, but the nice thing is that they're independent. So I will, if you get lost, there is some goldfish what you need to remember for the next step. Okay? Because I don't know, in Swedish you would say that you have like a memory like a goldfish. Is that the English expression? Okay, so elephant. Okay, because apparently goldfish
have good memories?
Yeah, that's the problem. So people think they have bad memories, but then I read about it and it's not clear if they have bad memories. So nothing bad against goldfishes. I don't know. Okay, so let's now answer ourselves. Okay, so laminar weighted instance, what do we mean? Okay, so I will show to you that we only need to consider edge weights of very special form. And we do that by, amazing power of LP duality. Basically, we will squeeze out as much as possible from LP duality we can. Okay, so to do that, we need to remember the problem and to define the linear program. So remember, we have edge-weighted graph. It should be output should be a connected set of edges, or a set of edges that connects the graph, and its Eulerians in degree equal to half degree. All right. So now the natural linear program formulation is that x uv indicates the number of times we traverse an edge. Okay. So now the weight of a tor is just the weight of an edge times the number of times we traverse it, so the sum of all edges. Now we have to ensure the 2 constraints, so it should be Eulerian and connected. So Eulerian means that the here I've written it in a compact form. So this means the sum of all the edges going out of vertex V should equal the sum of all the edges going into V. So the out degree should equal the in degree for every vertex. And then we want to avoid subtours, right? You don't want to have, you know, just a cycle curve. It should be a connected graph. So, for example, what you say is that for every set S, so let's say this is a set of vertices, you have to have at least two edges. One edge going in and one edge going out. So here I've used the notation that I have a set S. Delta plus V is a set of outgoing edges. Delta minus V is the set of incoming edges. Delta S is just the union. So you could have written delta plus S is greater or equal to 1 here. It's the equivalent. We just prefer to do it like that for some reason. I liked it. So what we are saying is that every out degree should equal in degree, and every set should have at least one edge going in and one edge going out. So in total, there should be at least two edges crossing the boundary of that set, if you think of it as an undirected cut. All right, so that's the linear program. So let's now see how we can get structure out of this. So I have an example instance. That's the instance I have. The numbers here is just the edge weights. Okay, so we have a linear program. So maybe we want to solve it. So solve the linear program. We get a solution depicted in black. So here I take this edge once, this edge 3 times, 1 and 2, 0, 1, 1, 1, 0, 1, 1, 1. Okay, so we were lucky, it's an integral solution. In general, of course, it's not integral, but to make my point, it's easier to draw, and to make my point is fine that it's integral. Okay? So we have some edge where the LP tells us something, often fractional, how many times we should use an edge. We have some edges that are 0, right? So the intuitively linear program tells you should absolutely not take this edge. So what can we do? Well, we can just drop these edges. Why can we just drop these edges? Because if we just drop these edges, we don't change the value of the linear program, right? The LP value is the same. And now if I find a Tor in the smaller graph, that will also be a Tor in the bigger graph. Okay? So I will get the same approximation in the bigger instance. Okay, so forget edges with LP value 0. It doesn't change the LP value, and any Tor is in smaller instance is a Tor in the original instance. Okay, so we just drop those guys. And let me now also, so this means that any remaining edge has positive LP value. Yeah. So let me just simplify the figure a little bit. Since I have an integral solution, let me just take 3 copies of this edge, 2 copies of this edge, so I get away with the black stuff. So this now depicts the primal LP solution. So now I want to have some structure, right? I wanted to say that, hey, on the remaining edges, I want to say that they have some special structure on the edge weights. Okay. Do these edges have any structure on the edge weights? So what could we say? I already gave away that we should use LP duality. So if I have an optimal primal solution, this is an optimal primal solution. If I take an optimal dual solution, right? I have complementarity slackness. So every remaining edge, which has the positive value in the primal, corresponds to a tight constraint in the dual. That's complementarity slackness. So if you have primal and dual optimal solutions, so x and y, if a variable has a positive value in the primal solution, it has to, the corresponding constraint in the dual has to be tight, and vice versa. So that's what we're going to do. Okay, so we know that all these guys have positive value in the primal, so somehow there's a corresponding tight constraint in the dual. So let's look. So this now, this is impossible to understand. So let's yeah, yes.
Make sure. Yes. So first of all, the LP weights, they could be fractional.
Yes, yes, of course, yes.
And you have an exponential number of
yes.
quality.
Yeah. That is a potential problem. So there's 2 ways of getting around that. One way is to formulate an equivalent linear program with more. So there is an equivalent linear program with more variables that has polynomial size. And another way is to do a separation oracle using ellipsoid. Here the separation oracle to verify that x is feasible is just to verify the mean cuts. You are saying that every cut in my graph should have value at least 2. So you can do that in polynomial time. But it's a good point. I don't know, so they have a very fast method for the pubs. for example. There they must do something smart. I guess, I don't know.
That's branch and cut, right?
Yes. So maybe they add I would guess they solve add constraints on the fly. Like, would be, for sure they don't run ellipsoid.
It would also be wrong. Did anybody check them?
Yeah.
I don't think anybody would check them.
Yeah, someone calls, I'm lost here. There's okay, good.
No, the computer, I mean, the computer approved.
Yes.
Okay. Check.
Okay.
Yeah. You don't know that visually.
If you care.
Yeah. No,
Okay.
No, it is very impressive.
John, someone had to count them all, if you want, instead of plus holes.
It is very impressive. Okay, okay. So dual variables. So let's try to understand the dual that I didn't explain. So it has two sets of variables. The first variable corresponds to the equality, the Eulerian constraint. So it has a vertex potential for each vertex, alpha v. That's for these constraints. You have a variable for each vertex. And you have a variable ys for each cut constraint. Okay? That's the two variables. You have a variable corresponding to each constraint here. Two sets of variables. And now what does this constraint says is that you have a constraint for every variable here. So constraint for each edge. It says that the sum of y values that cuts the edge plus the tail potential minus the head potential is at most edge weight. So let's just check this. So here I have a dual solution. On the vertices is the vertex potential. The vertex potential of this guy is 6, 2, 2. And here is the set S that has positive value. So this cut here has value 1, this has value 2, 4, 4. So this is an optimal dual value. So you can check that the dual value is equal to the primal value 22. So now I want to verify that this is a feasible solution. So let's look at this edge. So what did we have? We had the sum of cuts cutting this edge. So in this case, it's value 4, right? There's only one cut of the dual with positive value cutting this edge. So it's 4 plus the tail potential, 3 minus the head potential should be at most the weight. So the weight is 1. So it's 4 plus 3 minus 6 is at most 1. So it's equal to 1. Okay, good. Let's check another edge. This edge. So here the cuts are 2 plus 1, so it's 3. Plus the tail potential 4 minus 6 equal to 1. Good. So it's it's at most 1, but you can see that we are also correct with complementary slackness that everything is equality. So it's very good. Let's check this one. It's 2. Yes, 2 plus 2 minus 4. Okay, so it had value of 0. So it's very good. Okay. Here we have no cuts at all, so it's just that 6 minus 2 is equal to 4. Okay, so that's a dual. Over all possible solutions, it finds a dual that maximizes the sum of cuts, the fractional values of the cuts, 2 times the fractional values of the cuts. Okay? So now what could we say? Well, by complementary slackness, every edge in the graph has the corresponding inequalities type. So that means that the sum of ys crossing that edge plus alpha u minus alpha v is equal to the weight. So I could just move the potential to the right-hand side of this equality, right? I get the sum of ys is equal to the weight, uv minus the tail potential plus the head potential. Now that just defines a new weight function. So let me just normalize with these vertex potentials to get w prime. Okay. I define w prime to be the original weight function minus the tail potential plus the head potential. What can we say about the value of a torr for w with respect to the value of a torr for w prime? If you just look at the cycle, they have the same value, right? Because the potentials cancel out. Okay, so observation for any Eulerian edge at f, the weight of the original weight function is equivalent to the modified weight function. And this holds because if you can always decompose an Eulerian edge set into cycles. So let's just verify one cycle. The weight of this cycle in the new weight function is the original weight function plus alpha a minus alpha b for this edge plus the tail minus the head. Here you have plus the tail minus the head plus the tail minus the head. They just cancel out and you get the original. Okay. So you know, if I increase some potential, vertex potential, if it's minus when I enter, plus when I exit, and I need to enter and exit equally many times, this will cancel out. So this is actually very related to so neither nor Carp is here, so I can say. So how they use, how they calculate their lower bound for symmetric TSP. Basically, they will, I think they solve the spanning tree problem. For high degree vertices, they will increase the potential. For low degree vertices, they decrease the potential, and then resolve the spanning tree problem. So this is that's why it coincides with this linear program, because you find the right vertex potentials. Anyway, now we have a new weight function, and we can just, after normalizing with the edge weights. We have a new weight function after normalizing with the vertex potentials given by the dual. So we can forget about the vertex potentials. Okay? And in this new weight function that I draw here, the edge weight is just equal to the value of the cuts given by the dual. So that's what I did. Okay, so what happened? So we had a complicated structure. We solved LP, we dropped zero edges, we used complementarity slackness, and we normalized with vertex potential to get an optimal primal and dual solution x and y. Now alpha is 0 because we incorporated it in the objective in the weight, so that every edge weight is just equal to the cut values it crosses. So the weight of this edge now is 2 plus 1, so it's 3. The weight of these edges is 0 because there is no cut. Can I get some more structure out of this? So I only apply complementary slackness in one direction, right? From the primal to the dual. I can also apply it in the other direction. So you know, if I look at the positive dual values, meaning the cuts carrying some value, what can we say? Well, again, complementary slackness in the other direction says that this has to correspond to a tight constraint in the primal. So it means that every such set corresponds to a tight constraint in the primal. So it has one incoming edge and one outgoing edge. Or fractionally, it has one fraction going in, one fraction going out. All these sets that define the objective function has one incoming and one outgoing. Okay. And I drew this very nicely that the sets don't overlap, and that's not a coincidence. So by standard, this is what we discussed in the initial. So this was first done for the TSP in the 85 by Cornelius and others. You can uncross the dual. So they uncross the primal, but you can also uncross the dual so that no two sets carrying positive value overlap, have a non-trivial intersection. So they either contain in each other or they are disjoint. That's called a laminar family. So I drew it here, right? These sets form a laminar family because either two sets are containing each other or they are disjoint. And this you can assume. So that's all the structure we can get out, or we could get out of this. Okay. So that's what you have. So now you can so if you get lost, this is what you have to remember. So now we can define the instances. You don't have general edge weights. The edge weights are pretty special. So you are given a graph, a laminar family L of cuts, x and y. The set of cuts form a laminar family of tight sets, meaning tight that if I look at every set, there's one unit going in, one unit going out. So in this set, for example, there's one unit of edges, the fractional unit is going in, or fractional unit going out is 1. And the weight of every edge is given by these cuts. So weight of this edge is 2 plus 5 plus 1, which is 8. The weight of this edge is 1 plus 3 plus 2 plus 5. I don't know what is that. That's 11. And notice if I had an edge in the other direction, it's the same value. Okay, but the graph is not complete, right? So it's not a symmetric instance because you don't have the edges in both. But if the LP decided to keep both edges, they will have the same value. And this is what we call laminar weighted instance. And what we just proved is by doing complementarity slackness, basically, is that the row approximation algorithm for such an instance would yield a row approximation for general ATSP. Okay, row approximation with respect to the LP relaxation one. Should write here.
So where is the x in this formula? I just don't see it.
So x is just that x is tight on these sets S. So each set here is a tight set.
So the sum of the so x is indexed by vertices or
no, sorry. So x is a feasible solution to the primal,
which is just to the primal.
To the primal. Y is a feasible solution to the dual.
X is indexed by edges.
Edges.
Okay.
And every set in my lambda family is a tight set in the primal, meaning that there is one unit of x going in and one unit going out.
So this is a restriction just on the combinatorics of the sets, that there exists an x, because the x doesn't appear at all in the weights.
Yes. So
if I have a collection of sets, which are laminar in your definition, how do I know if there exists an x?
If there exists an x, well, I see. You could do okay.
Yeah. So
okay.
The x plays no role in the edge weights.
Exactly. X doesn't affect edge weights, but to verify, you could verify that exists an.
So if you really you want to formulate a collection of sets which are have this laminar structure for which there exists an x.
Yeah.
So not all collections, not for all collections there exists an x. What is the role of x here?
I don't see the. So yes, okay. So x is an optimal solution to the primal.
No, but now forget primal. You're describing to me a structure, a combinatorial structure, which is a collection of sets.
Yes. No. The combinatorial structure is the graph, the sets x and y.
I agree. But if you drop x from the story,
yes.
Then what? So if I gave you
you are telling me how to
collection of sets in weights y.
Yes.
If there exists an x for which this is.
I don't have a nice characterization, but I could solve the problem in polynomial time. That's just take the graph.
Of which laminar families admit an x.
Yes, probably. Like that's the constraints that you have to put to be equality in the primal.
There should be some sort of elegant combinatorial thing, so you can delete x from the picture.
Can we delete x from the picture?
It's a property of collection of sets that admit an x, which makes them tight. That's the only thing you need.
Oh yeah. Okay, so sorry. Okay, so let me try to answer your question. So we are given, I agree, so y, l, and g would define the edge weight and y.
Yeah.
Now, this is a good instance that we can work with if there is a solution to the primal.
There exists an x.
There exists an x.
So now there's a combinatorial question, which is which laminar families admit an x.
Okay.
Just purely combinatorial.
Yes.
Set systems.
Yes.
So there is no nice characterization of those set systems.
I never thought about it. So I don't know how to.
It seems to me like okay.
So by the way, there was this conjecture about these the fraction solutions that they are large coordinate x's with large values. Do you resolve that too, or?
Oh, there is a conjecture. I didn't know that existed. That we didn't.
Vempala paper.
Oh, okay. No, that I haven't thought about.
No, I really think it's worthwhile to try to. It could be that people who study set systems already have this kind of characterization of set systems, and then you're just deleting a quantifier from your definition.
Yes.
This is an x. You'll define. There's an intrinsic notion, and you're introducing a redundant variable with an existential quantifier, which you delete from the picture.
Yeah, I understand.
Using combinatorics of the family.
Yes. Okay. So, yes, we can look. I haven't thought of it. It's not so central here, right? But I agree the elegance. So, yes, for us we have so even to calculate what we need to solve the primal. So it's someone else for algorithm. It doesn't matter. But I understand what you're saying. I haven't thought about it. I cannot.
Do you have an example of a laminar family for which there is no x?
Yes. For example, suppose you have a graph that is not Hamiltonian. Then putting y to be all the singletons, there would not be an x.
Well, the existence of an x now is not related to y.
No, related to L. Related to L. Yes. So L. See all the singletons.
All the singletons.
Yeah.
Okay, you're right.
A graph that is not Hamiltonian, all the singletons, that would not be okay. Well, not Hamiltonian according to the LP. So the LP would detect that it's not, let's say a tree or something, like with a path. You know, the LP would not think it's Hamiltonian. A graph that the LP doesn't think is Hamiltonian.
The set system is what?
All the singletons.
All the singletons. This could be just a classical question in, like, you know, combinatorics.
No, this comes from combinatorics. These
No, I think there could be the same theorem saying consider a collection of sets who satisfies an axiom and all the y's and run over all the y's in this.
So sorry. So okay. I mean this was also basically known. So I should have lemma or. Is that okay? Okay. So let's continue. Okay, I agree that x is you can have a you don't need x in the definition. You can find an x satisfying this. Yes. Okay.
Actually, these days a common term is if it's been known for more than 10 years, it's folklore.
Okay, sorry, folklore. Helcop bound. So it's equal to 2 times. Remember, this is the dual optimal solution, so it's 2 times the value of the cuts. 2 times the sum of the values of the cuts. So in this case, 28, if you sum them up. That we will use later on. Okay, so that's what you had to remember. That now our, Asaf, you don't remember x, but otherwise we have to remember that we have these edge weights. Okay, good? So now I think it's new, but at the same time we can also agree that maybe the idea is not new. So we will this will make sense later on. So we will now say that we only have to look at very special instance of this form that we call irreducible. And the basic idea is very simple. So that is that we can do a recursive approach as long as optimum drops. And I will explain what I mean by this by taking a detour. So by looking at this very nice algorithm by Fiscal Alberto Maffioli. So I think this is a way people have tried to get this to be better than low base 2m, but so far without a success. So let me explain their algorithm and then explain what I mean by op drop. Then you can apply a recursive approach. So here, as I said, you forget about connectivity and let's just worry about Euler-unicity. So we find a cycle cover. Doesn't connect the graph, so now we contract. Well, the cost of the cycle cover is at most opt because it's a Tor is a special case. If you look at, yeah. Okay, so now you select one vertex in each set. Let's say the green one, and you repeat on this smaller instance, and you find a cycle cover. And then you select one vertex. It's again cost is at most opt because if you have the triangle inequality, you can prove that if I restrict myself to a few subset of the cities, the optimum has not a bigger cost. And now I have 2 components. I select representative in each component and I find a cycle cover. Okay? So that's their algorithm. So every iteration is at most opt, so you get 3 times opt. In general, you get log base 2 iterations because in the worst case, every cycle has a length 2. And this is what is super weird, right? You would expect that you don't always get cycles of length 2, so it should not be log base 2m. But it turns out that it's super hard to prove, and there are bad examples for naive, like some implementations of this approach. So that's what people try to push down the hidden constant by saying we don't select 2 cycles all the time. Maybe we select 3 cycles. Another way to prove that this is a constant factor approximation would be the following. Hey, when selecting the blue cycle cover, we made some progress, right? We have a smaller instance consisting on the green vertices. The optimum on the green vertices might be smaller than the original optimum. Maybe the opt dropped by some constant fraction. Like it's 0.99 times opt, or 3/4 times opt. And then we selected a green cycle cover and we have an even smaller instance. And the hope would be that the optimum of the even smaller instance is even smaller. So the optimum drop in each iteration.
So this is the kind of recursion you use?
Yeah, we will see how we implement this idea in our setting. So what if we had opt drops by say factor 9/10 after each iteration? Well, then we would be very happy and we would have a very nice constant factor approximation for ATSP. So this is a known strategy, I think. but no one has been able to pursue it. Okay, so we don't know if this is the case. Well, yeah, for some specific rules how to select the side cover is not the case, but of course one could come up with a smart way. So let's now see how we implement this, and to do that we're going to use the structure. Yeah, it's my jokes. So, so to use this, we're going to use a structure that we have a laminar weighted instance. And how can we define a smaller instance using this? Okay, so I will need two concepts. It's called the contraction and lift. So let me look at the contraction. So how can we get a small, here I have a laminar weighted instance without the edges. Remember that each set in my laminar family corresponds to a tight set. There's one input, one unit of x going in, one unit of going out. So one way of getting a smaller instance will be to identify such a set. Let's say this set. So it's one, here the fractional unit is 1 and one fractional unit going out is 1. I could just contract it, right? The standard graph contraction. I could replace this whole set by single vertex, which is now a tight set because I contract that tight set. Okay. Or I could take another example. I could take this big set S and I contract it into a single vertex. Okay. So that's just a standard graph contraction. So the edges that I obtain and the vertices I obtain in the new graph is pretty clear. What is not clear, right, is that I replace the whole bunch of y values here inside this set. So what is the y value I should set for the new set? Okay. Is it clear how I get a smaller instance? I take a tight set, like in my laminar family, I contract it. What I get is just to one point, to one vertex. So this is just the graph contraction, but now the question is how do I put this question mark, the weight? And to see that, it will be instructive to see how we're going to use it. So we get a smaller instance that we want to solve recursively. So that's what they call a lift. So we solve this instance recursively. We find a Tor in this smaller instance of good value, hopefully. Now we want to get a Tor in the original instance, right? So we call this, we want to lift it back to the original instance. Okay, so you walk here. You just think of it as walk in the O'Leary walk. So just starting here, 1, 2, 3, 4, 5, 6. I take the same edges. This is some edge going out of this set. 1, 2, 3, 4, 5, 6. But now these edges, right? I come in here and I exit there. That's a problem. So I come in one vertex, I exit in some other vertex. I wanted to have a connected O'Leary Tor. I want to have a sub-Tor. So I need to connect this vertex to that vertex. Okay? Yeah, so what to do? I mean, if I entered and exited the same vertex here, things would be great. In some sense, I would get a sub-Tor at least. But now I enter at one vertex, I exit at another vertex, so I have to stitch the Tor together. So the way we do is, I guess the simplest is just to add the shortest path. Okay? So we actually add a shortest path inside this set. Okay. I was ready that you find. So one has to prove that this path exists. Intuitively, why does this path exist? Okay, it's not too hard to prove, but intuitively, this is a tight set. So the LP value tells us that we should enter and exit once. But at the same time, the LP tells us that we should visit every vertex. So if we enter and exit once and we should visit every vertex, the LP basically should, at least there should be a path between every two vertices in this set. And that holds. So we add that shortest path, we continue, and we patch the thing together. So this is the sub-Tor we get, we call it lift. So this is not a Tor, right? It's guaranteed to visit every vertex outside the contractor set, but not every vertex inside. Okay? But at least it's a sub-Tor. So it's a starting point. So the way we're going to set the question mark is just the minimum value so as to guarantee that the lift we get is no more expensive than the Tor we get over here. This means that we're going to set the question mark so that it's guaranteed to pay for the rewiring we did inside. Okay? Does that make sense? I had to add some shortest path here, right? I have to pay for this shortest path. And I will set the question mark here so that we are guaranteed to pay for this shortest path. So that's so we always pay for the rewiring in the lift. All right, so let's see how we can do that. So we don't know how we're going to enter and exit this set. So we will actually look at the worst possible pair, the worst way of entering and exit, and that will give some cost. So what's the worst possible shortest path we have to add? So as an example, here I have, if I enter here and exit there, maybe I have to add this path. It actually crosses all the sets, so this is the worst possible cost, if you think about it. So this is the worst possible cost that path could have that I have to rewire. So it crosses this set, crosses this set, crosses this set, crosses this 3. So I would need to add 5 plus 2 plus 2 plus 1 plus 4 plus 3. So I would need to put this question mark to 17. Maybe, yeah. So so here there's one more thing that you have to prove. So you could think of the worst possible path. Maybe it goes in and out through this set, crosses this set many times. That would have much more cost than just what I said that had a cost of the sets inside this set S. So you can prove that's another thing you can prove is that there exists always a path between these green vertices that crosses, that enters each set only once. Okay. This is similar, you know, if you didn't have any sets, you only had vertices. That's the similar statement as saying there exists a shortest path between two vertices without a cycle. You can do that proof inductively. Okay. So here the whole values are not so important. What is important is that we have this contraction. The way we set the value, the question mark, is just to make sure that we can pay for the lift. And this fact here actually implies that the contraction never increases the LP value. If it increased the value, it's kind of a bad idea, right? Remember that the recursive approach worked as long as the LP value dropped. Here it's kind of a sanity check that we can contract and at least the LP value doesn't increase. Okay, so I had an example. So what is the first? Yeah. Maybe this is not so enlightening. Just think of it as the minimum possible way of setting this one so we are guaranteed to pay for the lift. Okay, so by design we have that the lift is no more expensive than a tour in this set. Okay. Okay. So just to summarize what we knew. So the contraction does not increase the LP value. Lift no more expensive than a tour, so it's great. The only bad problem is that the lift is not a tour. We are not guaranteed to visit every vertex inside the contracted set. So we have to still fix that. If it was a tour, we would have been done, right? Then just contract and solve recursively, lift it, and you find a tour in the original instance.
So lift you are referring to is what now?
Lift is, so we found a tour in a smaller instance. Yeah. The lift is the sub-tour that we obtain in the original instance.
Okay,
so by like just adding the shortest path. But it's not a tour, right? Because we might have missed out on some vertices inside this set. So that's what we have to fix to make the recursive approach work. So now we're going to use that if the LP value drops, we can solve the tour here, then lift it. It's no more expensive, but then we have some budget left that we can use to correct the tour inside the set S. So that's the recursive approach.
Where is this budget coming from?
I will show you.
I mean, it hasn't dropped by a significant amount.
It might not drop at all.
At all. And still you have a budget?
No. Then we call that's the irreducible instances. So we reduce it to the case when the budget doesn't drop at all.
Okay.
But those are very nice structure because think of it. If the budget doesn't drop at all, that almost means that there is a way to enter and exit that should visit all the vertices. Intuitively, because that means that we should enter and exit the shortest path as basically cost of the LP, meaning that the shortest path basically visits everything. So okay, if it doesn't drop, we cannot apply this, but we will. Yes.
Again, returning to the fractions.
Yeah.
Are we at some point going to show feasibility, or because you said we were done if every node was visited, we'd still be with a fractional solution.
Oh, good. So here I contract. I have some fraction solution obtained by the contraction.
Yeah.
I solve it, that means that I find an integral solution in a smaller instance. Like this here it's actually an integral solution I'm drawing. So it's an approximate integral solution in a smaller instance. Then I lift it to an integral solution in the original instance. So this would mean, this is actually an integral solution that I mean that I actually walk these edges. It's not a fractional solution anymore. So if this would have visited all the cities here, it would be a tour in the original instance.
But finding the integral solution in the smaller instance?
That you do by recursion. And the base case will be exactly the case that we discussed, that there is no set to contract. That results in a decrease.
So the initial set that you contracted, how did you choose that?
I haven't explained, but I will see. Okay.
And there is a reason why you have to contract multiple sets in this induction. Let's say multiple disjoint sets. And
you can do that. You can do that.
And that helps, or?
So let's. I don't think it helps here, but in the next, the other reduction, we do that. Okay, so implementing. So yes, so we just have to define what. So I will come back to your question, I think. So what we have to define now is that we can do this as long as our contraction is guaranteed to drop the LP value. And we define the set S as reducible if that guarantee is happening. Okay? So a set S is reducible if worst way to enter and exit crosses at most a weighted for 3/4 fraction of the sets. So in the worst case, it crossed all the sets, then there was no drop. So what I'm saying is that in the worst case now, it crosses only 3/4. This will allow me to set the new value of the contracted vertex to be strictly smaller than the LP value of the whole instance. Okay, so as an example, this worst case, it crosses all the sets. So it's not it's called what we call irreducible. Okay. Here, it only crosses some sets of total value 9, and the total value of all the sets were 12, so this would be just barely reducible. 9 is like 3/4 times 12. Okay. So this is just a definition for which sets decreases the opt enough. So now the theorem is, we say it's irreducible if no such a set exists. So a raw approximation for irreducible instances yields an 8 raw for laminar weighted and thus for ATSP. So we can just worry about instances for which has no set whose contraction decreases the LP value. So that would be the base case. So suppose I have an instance that I had here. I contracted there. So if I contracted this set, suppose now there is no set that will come about the decrease in the LP value. Now, if I had an algorithm for irreducible instances, I would get this tour. And then I would lift it back. I get a subtour, and I have to explain to you now how I complete it into a tour in the original instance. Okay. So yeah, so how do we prove that? Well, suppose we have an algorithm for irreducible instances. Okay, so let A be a raw approximation for irreducible instances. Okay, so I give you some you give me some instance. If it is irreducible, well, simply run A to get a raw approximation, which is better than 8 raw that I promised with the theorem. If it's already irreducible, there is nothing to do. So if it's not irreducible, that means that there exists a set for which if we contract it, it brings about a decrease to the optimal. There might be many sets. Which one should we select? So we select the minimal, any minimal set. Meaning that S is a minimal reducible set, meaning that any set strictly contained in this set is not reducible. This will be important. So a vertex is never irreducible. A vertex is never reducible. A singleton is never reducible. So this S will always be a non-trivial set. All right, so now we get that. So now we have 14 instead of 17 because it was reducible. You solve it recursively. Recursively, you use your 8 raw approximation solution on this smaller instance. This will have some budget. So what I claim is that this is some budget. The numbers here is not important. It's like opt minus whatever you dropped, right? Compared to the value. Here you have some LP value. Here you have another LP value. This is the new LP value. So I have 8 raw times the new LP value. That's old opt minus something. We will see what this minus something is later on. So this is my budget. So I have a lift. It's not a tour because I don't visit every vertex, but it's cheaper than what I need. So if I could complete this into a tour using the remaining budget, I would be done. Okay, so again, task complete tour while paying at most 2 row. 2 row times this 2 times. So what is this? So it's 2 row times 2 times the value of the sets inside S. That's how we defined it. We said that the drop should be proportional to the sets inside. So I will only explain how to do this in a simplifying assumption. If you want the whole proof, we should discuss afterwards. Or you ask me. So we need, okay, so remember we have a subtour. It visits all the verses outside the set S. It doesn't visit everybody inside S. So we have to fix S. The budget is basically the LP value inside S. 2 row times the LP value inside S. So now suppose, this is a heavy simplifying assumption, that the instance obtained by just forgetting about everything going out and in is actually a feasible instance. The X inside here, by just restricting inside, is feasible. Okay? So this is a feasible instance. That's a simplifying assumption.
Feasible for what?
So X, if I just look at X,
Feasible for
the primal, you know, X just
it clearly is not.
Yeah, it would have been a very special case because you have to like enter and exit the same vertices.
Yes, okay, sure.
Yes, it's clearly not in general. But for here, I think the main point gets across. So now it will be clear why I select the minimal, for example. So why did I select minimal? Because now every set here is irreducible. If one of them is reducible, I would have selected them before. So now I can use my, since S was a minimal reducible set, I'll count values 2 times the dual values, which is just exactly this expression here. So now applying my row approximation that we assumed that we had, we get a tour inside this set of value row times 2 times whatever we had before. That's the purple guys. So this is actually better by a factor 2 than we needed. So let's repeat what we did. We found a set, minimal set to contract. We recursively found a tour that we lifted that had value at most 8 row opt minus 2 row, whatever is inside. Then on the simplifying assumption, we found a tour inside S of this value. Okay? If I sum them up, I get a final tour of 8 row opt minus row times that. So I got a little bit better than what I needed. The reason I got better than I needed was this simplifying assumption. So in general, you lose another factor 2. Okay?
So in this, the additional edges are just simply you ignore the edges that you had from the list.
Yeah. So not
even caring that they're there, or you're not using them.
The way I visited here, yes, I ignore. Yes. I just impose a tour on S. Brand new tour on S. So in general, there are some complications. So S might not be strongly connected. So S, but then the strongly connected components, I impose a tour on each strongly connected component. And when I can prove that the lift has to visit each strongly connected component. Okay. So in the paper, we introduce an induce operator that is more complicated, that preserves the feasibility, that loses a factor of 2. But this is the main idea. Okay, so just contract as long as the LP value drops, lift it to a tour of the same value, complete it using the remaining budget. Okay. So now you can wake up. So that's all you have to remember. So now we finish this. So now we have reduced ourselves. So yes, maybe it's not like a 2-line, it's not like a pseudocode algorithm yet. So it's like more like a math paper, I suppose, that there's steps of reductions, and now we can forget what we looked at before. Now we have reduced our task to what we call irreducible instances. So let's now look at irreducible instances, try to solve those. So here I will be much less detailed because I think also we are running late. So here.
Yeah, 5 minutes.
Yes, so here, let me just explain. So now, so we call it, this was last you came up with this brilliant name, vertebrate pairs. So I didn't know what vertebrate means, but it's one of those.
But you knew it in Swedish.
Yes. I mean, yeah, and it's not the same word in Swedish. So here we will see that irreducible instances are very nice. Okay, why? Okay, so now I will do some simplifying assumptions. So L contains all singletons. So every vertex has some weight associated to it. And the instance is perfectly irreducible, meaning that there is no set that if I contract it, the LP value would drop anything. So the LP value would drop nothing if I contract a set. What does that mean? That means that the worst way to enter and exit a set has to go through all the sets in the laminar family. And in particular, since I assume that the laminar family contains the singletons, the worst way to enter and exit a set has to visit all the vertices. So that was the intuition why we felt like irreducible should be an easier instance. Because if a set doesn't bring about a decrease, the longest shortest path needs to be long. And in a perfect irreducible instance, the longest shortest path actually visits every vertex in a set. Okay. This is helpful, because this looks like here we might be able to do a Tor. So how do we do a Tor? So now suppose we have a perfect irreducible instance. Now I contract everything. I contract the maximal sets in my laminar family. That doesn't increase the value. The contraction never increased the value. Now I have a node-weighted instance, meaning that the only weights are on the nodes. That was the case we solved 2 years ago. So here I can apply the 28 approximation iron from that paper. I get a Tor that is 28 times opt. Now I have to lift it back. Okay. So now I have the same problem, right? That I enter and exit. If I only added a shortest path here, I might not visit all the vertices inside, right? So what I will do is to identify the worst way.
So for a node, intuition about a node-weighted instance, so how does a node-weighted instance induces edges and weight?
So the weight of an edge is just a sum. No, sum.
So it's symmetric in this case?
No, because it's not a complete, in this case it's symmetric.
Yeah, exactly.
But in general, the graph is not, I mean, not all edges are there, right? So it's a DAG. It's not a directed acyclic graph.
What is the direction? I mean, if you have an edge and the weight.
It's a directed graph.
The edges are directed, so you might not be able to.
Even if it was unweighted, right? If all edges have weight 1.
Oh, the weights? Okay. Yeah, okay.
It's not a complete graph.
I understand.
Yes. All right, so now in the lift, we just add the shortest path. We might not visit all the vertices. So what I will do is to identify the worst possible way of entering and exit. I first add a shortest path to the incoming vertex, the shortest path in the worst possible way, the longest shortest path, but since it was perfectly reducible, this shortest path has to visit all the vertices, and the shortest path to the outgoing. Now I do that here as well. I identify the worst possible way of entering and exit, shortest path to the entering, the worst possible that visits everybody, and that's how it works. Okay. And that's my Tor. This is the argument for perfectly irreducible. So it's actually that would be very nice if we could do that distinguishment that is either slightly reducible, but unfortunately, yeah. So we found the cost of the Tor was the lift, which is at most 28 times oft, plus the paths, and we can add that we can show that these 3 paths, since they have cost at most 3 opt. Okay, total cost is most 31 opt. So unfortunately, life is not that nice. So what we will find is what we call the backbone. It's not guaranteed to visit every vertex, but it's guaranteed to visit every set in our laminar family. And these instances, then we solve in the 4th step. I will explain that more on Tuesday. Or you can see Laszlo's talk on YouTube. He talks more about that and skips some. But intuitively, right, we have a right to some very nice structure where we could hope to solve the problem. Especially if it was perfectly reducible, we already solved it in this talk. Okay, so summary. So constant factor based on these reductions. Here we use just LP duality. Here we use the recursive approach. Here we use the node-weighted algorithm. And here we use circulations that I didn't talk about. So you can read one a day. This might need 2 days. That's why I skipped it. but it's not so complicated. So open questions. So I guess 2. So by this so you lose a constant in all except the first step. That's not the way to get 2. And even if we don't do it so modular, we get a couple of hundred. So here you really need new IDs. This is a problem I find interesting. So suppose you're given a complete graph. Now a graph is complete with distances that satisfy the triangle inequality. Find a Hamiltonian cycle with a minimum max weight. That's called the bottleneck version. So this has been solved for the symmetric case for several decades. There the right answer is 2. Our method doesn't yield anything for this. So the best guarantee for bottleneck ATSP is still given by the fin tree approach. So one can prove that the fin tree approach gives approximation guarantees here. So here is poly log log n. So if the what is called the fin tree conjecture, which I stated here, if this is true, then there exists a constant factor for bottleneck ATSP. So what is the fin tree conjecture? So is there a spanning tree such that for every cut, the number of edges crossing that cut of the spanning tree is roughly what the LP tells you. It's at most a constant times what the LP tells you how many times you should cross that cut. You need that for all the cuts simultaneously. So that will yield the bottleneck ATSP. I don't know if that's the case, if this holds. Then we don't know anything better than Christopher.
Is that obvious in the symmetric case? Or?
Yeah, so it follows because the square of a two-edged connected graph is always Hamiltonian. I don't know if that's a theorem, but I don't think I think one can prove it if one knows it's true. I think it's from the 70s or 80s. So here we don't know anything better than Christophidis even in the node-weighted symmetric case. So, thank you.
What was the question about that?
Yeah.